Have you ever stopped to think about how we teach a giant AI, something like ChatGPT, what we actually want from it? It's not like we're writing millions of lines of code with rules. Well, it's more like we're teaching it our values. And today, we're going to dig into a really cool breakthrough in this whole process. A simple but super powerful fix to a hidden flaw in how we align these massive models with what we humans actually prefer. So let's get right to the heart of it. The whole challenge of AI alignment, the whole shebang, really boils down to this one question. And we're not talking about good versus bad in some deep philosophical sense. We're talking about something much more practical. How do we teach an AI to give us answers that are helpful, that are harmless, and that actually match what we're asking for? All right, here's our game plan. First, we'll cover the basics of how we teach an AI our preferences. Then, we'll look at the two big methods for doing this, RLHF and DPO. After that, we're going to uncover a weakness they both share, introduce the clever new fix called IPO, and then wrap up by talking about what this all means for the future of AI. Okay, so let's start at square one. Instead of trying to hard code a rule for every single thing an AI could possibly encounter, which would be impossible, right? The modern way of doing things is way more intuitive. We just show the AI what we like better. And this is done with something called pairwise preferences. Seriously, it's so simple, it's brilliant. You have a model generate two different answers to the same question. A human then looks at both and just picks the one they think is better. Is it answer A or is it answer B? That's it. And when you repeat that simple choice millions of times, you build this massive data set that captures a slice of human values. So the first major technique that really harnessed all this data is called reinforcement learning from human feedback, or you'll see it as RLHF. This was the powerhouse method behind models like InstructGPT, and it was a huge leap forward in making AIs genuinely more helpful. You can think of RLHF as a two-step dance. First, you take all that A versus B data, and you train a totally separate AI called a reward model. Its one and only job is to get good at predicting what choice a human would make. Then, for step two, you use that reward model as a kind of automated coach for your main AI. Every time the main AI generates a good response, the reward model gives it a little virtual pat on the back. So what's the magic making this all work? Well, under the hood, RLHF relies on something called the Bradley-Terry model. The best way to think about it is like the ELO rating system for chess players. You know how that system takes a simple result, player A beat player B, and turns it into a numerical score for each player? This model does the exact same thing, but for AI responses. It turns response A is better than response B into a concrete reward score. Now, RLHF works, but man, it is complicated. You have to train and then maintain two of these enormous separate AI models. It's a lot. So researchers started thinking, could there be a simpler way? And that led to a more streamlined approach called direct preference optimization, or DPO. DPO was just this brilliant insight. Researchers figured out that they could do some clever math to basically rearrange the entire RLHF formula and cut out the middleman. With DPO, you don't need that separate reward model anymore. You can train the main language model directly from those raw A versus B preference pairs. It's way more stable, it's less complex, and often it gets you the same, if not better, results. So DPO sounds like the perfect solution, right? Simpler, faster, better. Case closed. But as researchers at Google DeepMind started digging deeper, they found that both DPO and the original RLHF method actually share a really subtle but pretty critical vulnerability. And the folks behind this new method put it perfectly. They found that both of these approaches can overfit. And this happens especially when the preferences are deterministic. Now, that's just a fancy way of saying when one answer is always better than the other. And this is where things get a little weird and kind of counterintuitive. To really get why this happens, we have to talk about something called KL regularization. It's a crucial piece of the puzzle. See, when you're fine-tuning a model, you don't want it to completely forget everything it already knows about language. So you use this KL term as a kind of safety leash. It anchors the newly trained model to the original one, and it keeps it from drifting too far off and becoming, super weird or extreme. And here is where that safety leash gets yanked. The math behind all these methods, it kind of assumes that preferences are probabilistic. Maybe answer A is better 80% of the time. But what happens when the data is just obvious? Like when a helpful, safe answer is always better than a harmful one. 100% of the time, no ambiguity at all. This mismatch between the math's assumption and the data's reality is exactly where things break down. When one option always wins, the math tries to give it an infinitely higher reward score than the loser. And this infinite signal is so powerful, it just completely overwhelms the safety leash. The model overfits like crazy, learning to assign 100% probability to the winning answer and completely ignoring everything it knew before. The leash just snaps. So, how do you fix a snapped leash? Well, this is where the researchers proposed a really elegant solution. It's called Identity Preference Optimization, or IPO. IPO is just incredibly elegant. It doesn't add more complexity or more moving parts. Instead, it just changes the underlying math of the objective function. Instead of chasing a reward score that can shoot off to infinity, it works with the preference probabilities directly. This one tiny change puts a natural cap on the reward signal. It literally can't go to infinity, which means that safety leash, our KL regularization, always keeps its grip, no matter how clean or one-sided the data is. And the difference is just night and day when you look at a simple test case. So imagine one action A always beats another action B. While DPO just collapses, it overfits and learns to assign a 0% chance to ever picking the losing action. But look at IPO. It's totally different. It still learns the preference, for sure, but it respects that safety leash, keeping the probability for the losing action above 0. It stays balanced. This bar chart from the paper just makes it crystal clear. That reference bar on the right, that's where the model started. Now look at DPO in the middle. It goes completely off the rails, shooting the probability for the winning action all the way up to 100%. That is classic overfitting. But IPO is so much more sensible. It increases the probability of the winner, which is what we want, but it stays regularized and much closer to the original. The safety leash is doing its job perfectly. Okay, now this might seem like a really small, technical, in-the-weeds kind of fix, but believe me, its implications for building safe and reliable AI in the future are actually pretty huge. So why does this matter so much? Well, first off, IPO is just more robust. It handles that clean data without breaking. Second, it's safer. By not letting the model assign a 0 probability to things, it keeps its options open, which is super important when your data is sparse. And, maybe most crucially, it makes that safety leash actually work like a control knob. Developers can turn the dial on regularization and get a predictable outcome, something DPO just couldn't promise. And it does all of this while keeping that beautiful simplicity that made DPO so great in the first place. And here's the real takeaway. Progress in AI safety isn't always about building bigger, more complex systems. Sometimes it's about finding that one single elegant change in the foundation that makes the entire system more stable by its very design. And really, that's what IPO represents. It's a huge step away from a method that just sort of works, and toward one that's built on a much more solid, more theoretically sound footing. And that's how we get AI systems that are not just more powerful, but also more predictable and more safely aligned with what we want. So this leaves us with a final thought to chew on. As these AI systems keep getting more and more capable at this exponential rate, our methods for steering them have to become just as robust. Will these kinds of elegant, mathematically grounded fixes be the key to making sure that AI stays safely aligned with humanity? It's probably one of the most critical questions we face as we build out this future.